Okay, guys, next set of notes. We've talked about vectors when we did the vector lab. So now we're going to talk about the motion, two-dimensional motion when it's projectile motion. So first, what are we doing and what is projectile motion? So you use components, your X and Y components like we did in the lab, to simplify calculations. So we're going to add the vectors because it's easier than multiplying vectors. So think back of what we did in the lab. So projectile motion is the motion of objects moving in two dimensions under the force of gravity. So that would make the projectile what item or object that's been launched. So imagine in your mind's eye, you're going outside, no cars around, no kids around, no dogs, whatever. You pick up a rock and you throw the rock. Okay, everybody, I assume, sometime in their life has thrown something. Okay, it follows a path. You throw it, it goes up, and then it comes down. Okay, the object, the rock, whatever you threw, your cell phone, whatever it is that you threw, is the projectile. The motion of that object is the projectile motion. The path the projectile took, the going up and then coming back down, is a parabola. Think about a parabola that you talked about in math class. Okay, so for this exercise or train of thought, we're going to ignore air resistance for now. So you throw something, it goes up, makes this arc, and then it comes down. Okay, any horizontal velocity means the object has horizontal motion. So it's going someplace. Think of your XY axis. A projectile has an X component because it is traveling from you to wherever it lands. It also, okay, for the horizontal velocity means an object will have horizontal motion. For our purposes, horizontal velocity is going to remain constant. So air resistance would slow it down. We're going to assume it stays constant. Projectile motion is also free fall with an initial velocity. Okay, we throw it, it has an initial velocity, but as it goes up, it comes back down. Okay, it has a y component. An object in free fall and a projectile released at the same time from the same height have the same vertical velocity. It would hit the ground at the same time. Okay, this is hard to imagine, but think back. Okay, if all objects fall at the same rate, remember we saw the feather in the bowling ball video. If I'm on a cliff and I throw a rock off the cliff, at the same time, if I throw it straight out and down, at the same time, I am going to release another rock. So I release a rock and I throw a rock out and it goes down. They are going to land at the same time. You'd want to think that the one that you just dropped is going to fall, is going to hit first. That's what you want to think. But because all objects fall at the same rate, it is in free fall, even though that it's thrown, they both land at the same time. Okay? Trust me, they do. And if I can think of a lab that we can do, that you could do at home, I will have you test that out. Okay, so vertical motion of a projectile that falls from rest. This is the case when you're on the cliff and you just drop the pebble, you drop the rock, okay? The vertical motion is this set. Oops, sorry, flipped it too soon. So your y component, your y motion, your velocity, is going to be g, which is still 9.81 meters per second squared, times how long it took. These formulas should look very familiar. These are the same formulas that we have used before. The velocity, if you don't know time, but you know the height, your delta y is your vertical component. So if you know the height, you always know g, you can figure out the velocity, the final velocity when it falls. So when it hits the ground, how fast is it going, whatever it is. So it's 2 times g times the height, okay? And if you're looking for the height that something fell from, it's 1/2 times g times the change, how long it took squared. Delta t is how long it took. Okay. If you want to calculate how far from the cliff it landed, so the horizontal component, okay, you can use delta x is going to be your x velocity times delta time, okay? And so your horizontal velocity is going to be the same as the initial velocity in which it's thrown. If something is thrown at 2 meters a second, its horizontal velocity is going to be 2 meters per second. Okay. If you know your x's and your y components, here we go again, we're using Pythagorean's theorem. You can use Pythagorean theorem to find the velocity at any point on the projectile's path. Okay, and this is what we're going to do. There is a kind of a lengthy sample problem I'm going to step you through. Put it in your notes, because we're going to be doing some similar to this tomorrow when I give you the problem set for projectile motion. Okay, so go ahead and put this in your notes, and then you will have these notes also when you take the test over this unit, because they're open note test. That's a very strong hint that a problem like this will be on the test. Okay, the Royal Gorge Bridge in Colorado rises 325 meters above the Arkansas River. Suppose you kick a rock horizontally off the bridge. Standing on the bridge, you kick a rock. The magnitude of the rock's horizontal displacement is 45 meters. Okay. Find the speed in which the rock was kicked. So you kick the rock off the bridge, it lands in the river 45 meters away from the bridge, but way, way down, okay? So it's had a long, that bridge is really tall, that gorge is really deep. I've been there. So find the speed in which you kick the rock, okay, in order for it to land 45 meters out from the bridge when it finally hit the river. So here's your little stick person. Always helps to draw the diagram. Draw you a diagram. Here you are, you kick the rock. You kick the rock out and it comes down. It's in free fall. Gravity's working on it. There is a horizontal component, which is how far away from the bridge did it land. And there is a y component. How tall is the gorge? How tall from, or what's the distance from the river to the bridge in which you were standing? So you know that delta y, the change in the vertical, is 321 meters, and it's negative because it's going down. Okay, think if this were an xy coordinate, the origin would be where you're standing. You're at the origin. Okay, so it goes down technically into the fourth quadrant. Okay, so delta y, negative 321 meters. It lands 45 meters away from where you're standing, just way, way down, okay? Gravity, 9.81 meters per second squared. It's negative because it's going down. We've covered that. And it wants you to find your initial velocity, the velocity in which you kicked it. How fast did it come off your foot? Meaning, how hard did you kick it? Okay, so your delta y, your velocity x, your velocity initial is going to be the same as the velocity associated with this x component. That's what you want to find. How hard did you kick it? How fast was the rock moving right as you kicked it? So, delta x, okay, or velocity x, the velocity of x is going to be the distance in the x direction divided by how long it took. And that's going to give you time. Okay, so we rearrange this equation and we're going to solve for delta t is going to be the square root of 2 times your y component divided by g. This is an equation that we used before for free fall acceleration. Okay. Delta t equals the square root of the whole thing here, 2 times delta y divided by g. So 2 times the height, negative 321, divided by g. This negative counts out this negative, so it's 2 times this divided by this. Take the square root of your answer, and you get it took 8.04 seconds from the time you kicked it to the time it landed in the river. It took 8 seconds. Okay, I'm trying to move this around. There we go. Delta x, I keep saying that, velocity x is equal to the delta x, the distance it landed out, divided by time. So here we go. 45 meters. It landed 45 meters out. We just calculated the time. It took 8 seconds. So your answer, your initial velocity in the x direction was 5.56 meters per second. Okay? We're pulling back and reusing the equations that we used in previous chapters. So we're going to be using the free fall equations, which some of them also came from motion in one direction. Okay, so look back in those notes. You're going to be using those again. Okay, next question. Projectiles launched at an angle. You must take the angle into consideration for these calculations. So we're going to be using sine, cosine, and tangent again. This is why it's so important for you to draw the picture of the equations, of the sample of the problem, so that you know what you're actually looking for and what you have. Okay, the velocity in the y direction, the final velocity is going to equal the initial velocity multiplied by the sine of theta plus g times how much time it took. The final y velocity squared is equal to the initial velocity times the sine of theta squared plus 2 times g times delta y. These should look very familiar, except we're throwing in a kink in the fact that we have an angle now. Okay? Instead of going straight up or straight down or side to side, we're now launching things at an angle. This would be like you throwing the rock and making the parabola. There's an angle between the ground and that rock that is launched if you threw a rock. Okay? You're not throwing it straight out and you're not throwing it straight up. You're throwing it out in front of you at an angle. And that's what we're going to address right now. Please make sure these end up in your notes. You will see these equations again and you will need them to work the problem set. Okay. A zookeeper finds an escaped monkey on a pole. While aiming her tranquilizer gun at the monkey, she kneels 10 meters from the pole. Okay, in your mind. Monkey on a pole, zookeeper kneeling on the ground 10 meters from the pole, which is 5 meters high. The tip of her gun is 1 meter above the ground. At the moment the zookeeper shoots, the monkey drops a banana. The dart travels at 50 meters per second. Will the dart hit the monkey, the banana, or neither one? So what kind of shot is our zookeeper? Will the tranquilizer dart hit anything? So, and I admit this is kind of a convoluted sample question, and I probably will not give you something this complicated on the test, but if you can understand what we're going to go through on this one, you shouldn't have any problems with the rest of this chapter. Okay, here's the picture. Here is the flagpole. It's 5 meters from the ground. The ground is here. It's not marked. The zookeeper is kneeling down. The tip of her gun is 1 meter off the ground. So here's basically the tip of her gun right here. So 10 meters, X is 10 meters right here. G is always G. The velocity, the X velocity, the initial velocity of the dart was given at 50 meters per second, and delta Y is 4. Because remember, the flagpole is 5 meters. The tip of the gun is 1 meter off the ground. So the monkey is basically up here, and there's 4 meters. This is level with the gun tip, the tranquilizer gun, and then this is the 1 meter where the zookeeper's kneeling. So we need to find this angle. Okay, so you know opposite is 4. You know adjacent is 10. Okay, 4 and 10. You can do the inverse tangent. Just plug and play. Opposite over adjacent. So 4 divided by 10, inverse tangent. So this angle right here is 21.8. Don't give up yet. So 5 meter flagpole, the tip of the gun is 1 meter off the ground. So that means this part of the flagpole is 4 meters and this part of the flagpole is 1. You want to find this angle. You're given this is 10, you know this is 4. Inverse tangent is opposite over adjacent. 4 divided by 10 and then go inverse tangent. And you get 21.8. Now you got to find out the Y. Okay, so now you know the angle. Now you need to know delta Y. Okay, so 1/2 times G times time squared. We've known this. Rearrange this equation to solve for time. Okay, time is also going to be equal to delta X divided by your initial velocity times cosine theta. So time is going to be your 10 divided by the 1/2 G. Okay, let me back up. The initial velocity, 50 times cosine theta, which is the 21.8. So use this equation to find time. Time equals your X, which you're 10 meters away from the pole, divided by your initial velocity, which you shot the gun at 50 times the cosine of the angle we just calculated. So the time is 0.215 seconds. That's how long from time she shot the dart until it hit something, maybe. Okay. Now, your y component, back from, is 1/2 times g times delta t squared. We know this. We always know g. We just calculated time. So your y component is negative 0.227 meters because it was launched okay? The dart was launched like this, and it came down, and maybe it hit something. This is for the banana, okay? For the dart, the y component is the initial velocity times sine theta times delta time plus 1/2 g times time squared. You know all this. We just calculated it. We calculated where the banana was at a certain time. Okay, it had dropped 0.227. The dart, okay, we figured out that it was going to hit something at 3.76 meters. The banana fell this far. The dart rises this much. The banana is this much above the ground. The dart is this much above the ground. So the dart hits the banana. Now, I realize that you're going to have to actually look at that for a while, okay, for that to make sense. I promise not to confuse you that much on the problems that I'm going to have you work. But if you can figure out this one by looking at the solution, like I said again, you're not going to have any problems. So that's the end of the projectile motion. The main point I want you to realize that when there is projectile motion, when you throw a rock outside, the rock goes up, it's a projectile, it comes back down, it makes this arc. There is an x component on that arc, and there is a y component on that arc. Okay? If you know the x and you know the y, you can figure out the velocity or the magnitudes using sine, cosine, and tangent. You can also find the angle in which you threw the rock compared to the ground, okay, or to the horizontal. So, and this is what we're going to be doing tomorrow. So, I am not going to leave you stranded. Whatever problem set that I assign you, I will do another short video to get you started. So don't panic, get your notes done, take a picture, and send them to me. Thanks, guys.